Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. This video lecture is the continuation of our previous one. Here we are going to discuss about the classes of digital filters. Here we have two main classes. One is finite impulse response filter, another one is infinite impulse response. In this finite impulse response FIR, which is non-recursive, in the form of y of n, which is equal to h of 0 x of n plus h of 1 x of n minus 1 plus h of n x of n minus n, with n being the order of the filter. Here the main advantage is always it is stable, the phase can be made exactly linear, we can approximate any filter we want. And the main disadvantage is we need a lot of coefficients n large for good performance. And infinite impulse response, which is recursive of the form, see here, y of n plus a1 y of n minus 1 plus a n y of n minus n, which is equal to b naught x of n plus b1 x of n minus 1 plus etc. plus bn x of n minus n. Here the main advantage is very selective with few coefficients, and the disadvantage is not necessarily stable non-linear phase. See finite impulse response filter, a filter whose impulse response has finite duration, which is called finite impulse response filter. Here see, our input is x of n, output is y of n, and your filter function is h of n. See the output. Here the outputs are in discrete form, because in biomedical signal processing we need to convert our continuous analog signal into discrete signal. With the help of quantization or round off, we'll convert those discrete values into digital values. So our signal representation always in terms of discrete. See, our input x of n, output y of n, and our impulse response function h of n. Here h of n is 0 in the left negative side and positive side. In the mid we have values, signal values. See, I'll have sample problem. Here the problem is, given a desired frequency response h d of omega of the filter, determine the impulse response h of n. Here we have to relate the frequency response and the impulse response by the dt of t. Here the formula is h d of omega, which is equal to dt of t of h d of n, which is equal to summation n equal to minus infinity to plus infinity h d of n e power minus j omega n, h d of n, which is equal to I dt of t of h d of omega, which is equal to 1 by 2 pi integral minus by 2 pi h d of omega e power j omega n d omega. Example, ideal low pass filter. See here, the hd of n becomes hd of n, which is equal to 1 by 2 pi integral minus omega, here integral minus omega theta 2 plus omega theta a e power j omega n d omega, which is equal to a sine of omega c n by pi n, which is equal to a omega c by pi sinc of omega c pi n. Here the output becomes, see here, hd of omega, which is represented in terms of amplitude and frequency with a range of plus omega c to minus omega c. Here our theta value becomes plus omega c to minus omega c. And finally dt ft of hd of omega, which gives the value hd of n, which is an impulse signal. See here, this curve, this example, it shows the figure for omega c, which is equal to pi by 4. See the diagram, which is our output h d of n. See here we have to consider two facts. First one, the filter is not casual. The impulse response h of n is non-zero for n less than 0. The impulse response has infinite duration. This is not just a coincidence. In general, the following can be shown. If a filter is casual, then the frequency response cannot be 0 on an interval. See here, see the example. Here the magnitude and phase are not independent. They cannot be specified arbitrarily. Here the consequence is, an ideal filter cannot be casual. See the values of h of omega, which is equal to 0 in low conditions. But the consequences is an ideal filter, it should not be 0 and it cannot be casual actually. See. And next problem is to determine a casual finite impulse response filter, approximation of the ideal filter. We'll see this in next class. Thank you.